Okay, from now on, we're gonna look at two representative random variables which are continuous. The first is exponential random variable, and the next is the Gaussian random variable. So first, let's look at the exponential random variable. So exponential random variable has a one parameter. Typically, we use the notation lambda. And a random variable is called the exponential with lambda if its PDF has this form. Okay. Lambda e to the minus lambda x. So it looks magical at first glance, but this exponential random variable has this kind of form where x is very small, then we have a higher probability, and it kind of decays exponentially. And as you can expect, for the large lambda, we have a more aggressive decaying pattern than the small lambda. Okay? When the x is 0, then the value of PDF is lambda, but its decaying pattern is a little bit different, like more aggressive or less aggressive, because of this lambda parameter. Anyway, this is an exponential random variable. We're interested in the CDF, which is an integral from the 0 to x of this PDF. And if you do that, like very basic integration, like this, and it's minus 1. So this is the CDF of exponential random variable, and the CCDF is obviously 1 minus fx is equal to the e to the minus lambda x, which is a very simple form. Okay, so CDF and the CCDF has the following form, and the next what we need to do is that we're interested in the expectation and the variance, okay, of exponential random variable. So let's do that. All right, so the expectation is the x multiplied by the PDF, which is a lambda e to the minus lambda x. And in order to do the integration, we're gonna using the technique of the integration by parts. So in this case, this is u and this is dv. So this is u, and this is the integration of this guy. So the lambda minus lambda e to the minus lambda x. Okay, that's why we have minus e to the minus lambda x. And v du, so v is minus e to the minus lambda x, and du is 1. But here we have minus, so minus, and so it becomes plus. Okay, that's why we get this. All right. And the from 0 to infinity, so if we plug into the infinity, then it becomes 0, and 0 minus 0, so 0 minus the integration of this guy is minus lambda e to the minus lambda x from 0 to infinity, and infinity goes here. That's 0 minus lambda over 1. Okay, so that's why 1 over lambda. All right, so we have the expectation is 1 over lambda, and we can apply the similar technique for the expectation of x squared. Again, we're going to use the integration by part, and this is u and this is dv. Okay, all right, so this is the uv from 0 to infinity, and this is the v du, right? So du is 2x because the u is x squared, and the minus is the plus e to the minus lambda x. Okay, okay. Now this is a 0. Okay, now for this, rather than we do the integration again, we have this result. What we can do is that we are using this result. So multiply by lambda divided by lambda. Okay, so which is equal to the lambda over 2 lambda e to the minus lambda x dx. And we know that this is expectation of x. That's why we get this. And expectation of x is 1 over lambda, so 2 over lambda squared. So the variance is expectation of x squared, and the square of expectation, so it's 1 over lambda squared. So this is the variance, and this is an expectation of the exponential random variable. Good. Okay. So going back to the CCDF. Well, CCDF has this following form. because the CDF was 1 minus e to the minus lambda x. Okay. All right. So if we look at this CCDF, the probability that x is larger than x is some decaying function where 0 is equal to the 1 and exponentially decaying. Okay. So when we have this kind of CCDF of exponentially decaying function, you can see that this random variable is very appropriate for modeling a waiting time, because we don't want the long waiting time. The short waiting time, we have a higher probability, but as the waiting time becomes larger and larger, we have a very small probability, so it exponentially decays. So this kind of form of the CCDF can motivate us to use this random variable as the waiting time until some incident of interest take place. Okay. So for example, like what is the message arriving time at a computer? I need to wait a message. Sometimes some equipment breaking down, okay? A light bulb burning out. Those are all the waiting time. So in order to model this waiting time, we often use this exponential random variable. But wait, with waiting time? Well, there was some discrete random variable which models the waiting time, right? And that was a geometric random variable, if you remember. So one may ask question is that what is the relationship between the exponential random variable and the geometric random variable? And we know that the geometric random variable is defined for the discrete case, and here the exponential random variable is for the continuous case. So we can expect some kind of relationship, right, between those two random variables, and now we're going to look at those things soon. But before looking at that, let's first look at an example of how the exponential random variable is used. Okay, this is an example. So suppose that a very small meteorite first lands anywhere in Korea, for example. Okay, and well, the meteorite landing time, that can be regarded as some kind of waiting time. So we're going to model this time of the landing using an exponential random variable, and the mean is 10 days. Suppose that the current time is midnight, and I'm just wondering the probability that the meteorite first lands sometime between the 6 a.m. and the 6 p.m. of the first day. Okay. How can we compute this probability using the fact that my time of the landing is modeled as an exponential random variable with the mean of 10 days. Okay, seems not very difficult, but just pause the video and try to answer this question. Okay, so let's solve it. We know that the expectation of the exponential random variable is what is the 1 over lambda. And the mean is 10 days, so 1 over lambda is 10. So the lambda is 1 over 10. Okay, so we figured out the parameter of the exponential random variable, which is lambda, and that's 1 over 10. Current time is the midnight, so 6 a.m. from the midnight is in terms of the day, that's a quarter day. Similarly, the 6 p.m. from the midnight is the 3/4 day, 3 or 4 day, right? So the question is that the probability that the landing time is between the 1 over 4 and 3 over 4. This is 6 a.m. and this is 6 p.m. Since we know this distribution of the CCDF, because CCDF looks very simple, so this probability is equal to the probability that x is larger than the 1 over 4 minus x is probability that x is larger than 3 over 4, right? And that is equal to the probability that x is between the 1 over 4 and the 3 over 4. And using this equation, then that's e to the minus 1 over 40 and minus e to the minus 3 over 40, because the lambda is 1 over 10. Okay, and if you run the calculator, then you can get this this probability. Very nice. Going back to the relationship between the geometric and an exponential random variable. So in order to look at those relationship between those two random variables, let's first look at how we model a system evolution over time. So suppose that you want to model some system, like whatever, some machine or some computing behavior, anything. So we can model a system evolution over time using the two ways. First is we're gonna consider the time is a continuous thing, or sometimes time is a discrete thing. This is just a modeling issue. It's not about which is wrong or right. It's a modeling issue. For example, suppose that I want to track the customer arrivals at my shop. And there could be two modeling approaches. First modeling is that, okay, in every 30 minutes, I will record the number of customers for each 30-minute window. The first 30 minutes, second 30 minutes, 2 people, 3 people, and 4 people, and so on. That's one way of modeling the customer arrivals at my shop. The second modeling method is the continuous time, meaning that I'm gonna just record the exact time of each customer arrivals. Of course, the modeling 2 looks more exact than the modeling 1, but modeling 1 is one way of modeling the customer arrivals. Now, in modeling 1, rather than recording the number of customers every 30 minutes, what about every 10 minutes? What about every 1 minute? What about every 1 second? What about every 0.0000001 second? Now, one can easily conjecture that if you record the number of customers every like 0.0001 second, it's almost equal to the modeling 2, right? Because the granularity of time is really small. That is equal to the almost to track the customer arrivals at the real time, like continuous time, right? So what is my point? My point is that in many cases, continuous case is at some time of the limit of its corresponding discrete case. So whenever we model a system evolution over time, there are two choices, but somehow they resemble each other. And we can regard the continuous case as some kind of limit of the discrete cases. And as you can expect, then the exponential random variable looks like as some kind of a limit of the geometric random variable, because geometric random variable is defined for the discrete case. So the question is that, can we mathematically describe how the geometric and random variable meet each other in the limit? So in order to do that, we're going to first define the word slot. And the slot is nothing but a one-time unit. So as you can imagine, I define this slot because this slot can be used for the discrete random variable, because discrete random variable is used in terms of the discrete times. So this slot can be anything depending on your modeling. It can be 1 hour, it can be 30 minutes, it can be 1 minute, or it can be 10 seconds, depending on how you use this discrete time. Okay? So once you define the slot, the continuous system can be regarded as intuitively the discrete system with the infinitely many slots whose each slot's duration is infinitely small. Again, going back to the example of the modeling of the customer arrivals at my shop, if I record the number of customers at every like 0.00001 seconds, it seems equal, almost like equal to the continuous case. Okay. Now remember, if we do this, like if we decrease the slot size, for example, to an arbitrarily small thing, then the success probability over one slot, which is used for the discrete random variable like geometric random variable, it should also decrease to the very small number in the limit, right? In order to make a balance.
by making balance means that the mean number of arrivals should be sustained as a constant. Then since we are increasing the number of slots, the success probability, the P over one slot, should decrease. Okay, that's the intuition. So what we're going to do is this. So given the exponential random variable with the parameter lambda, I'm going to construct a geometric random variable which is parameterized by the delta, where I'm going to use the notation like x delta geometric, where slot length is equal to delta. So here's this delta is the parameter. So that's why I use this parameter in the notation. And we're gonna set the success probability over one slot, which I denote P delta because delta is a parameter, to be that's 1 minus e to the minus lambda delta. I know that this looks very magical, whose secret will be uncovered soon. But note that this P delta goes to 0 as delta goes to 0, right? Because as delta goes to 0, this goes to 0, so this goes to 1, so P delta goes to 0. So as delta goes to 0, then the probability of success or customer arrival, whatever, goes to 0. That's my setting. That's my construction. Okay? And first we need to remember the fact that the probability that my geometric random variable x delta geo is less than or equal to n, and that is equal to the 1 minus p delta to the n. Oh, why is that? Do you remember that the PDF and CDF of geometric random variable with the parameter p? Yeah, the PDF was 1 minus p to the what? K minus 1p. And the CDF was actually 1 minus p to the k. That was the CDF. That's why we are using this. If you are not comfortable with this thing, so you can just do the math of the geometric random variable of using the PDF, and you can compute the CDF. Okay. So because of my construction of the P delta, plug this into the here, then it turns out that we get this probability. That's my construction of this geometric random variable. All right, good. So what we can do is this. So note that the probability that CDF of exponential random variable is again 1 minus e to the minus lambda x. That's what we have did. Okay. So what I'm interested in is that I'm going to look at the CDF values for a very specific set of the values of the x. I'm interested in what happens to the CDF of the exponential random variable lambda, 2 delta, 3 delta, 4 delta, and so on. Generally n delta. So obviously if I plug in n delta here, the x, and that is equal to the 1 minus e to the minus lambda delta n. Oh wait, this probability is equal to the, from the previous slides, is equal to the probability that the x delta geometric is less than n. And again, this relationship is coming from my construction of the P delta. All right, okay. So it means that when the x is delta, 2 delta, and 3 delta, and so on, this random variable and this random variable behave similarly. Here in this geometric random variable, what I'm interested in the probability that my geometric random variable is less than or equal to n, because it's just a count a number of time slots. And that is equal to in the continuous case, the exponential random variable is less than or equal to x. Whenever x is n delta, then this probability becomes equal. So in a graph, we can see this kind of form. So this one slot length is delta, I need to use this is delta, like here. All right, now this is a delta, and this is 2 delta, and this is 3 delta, and so on. So whenever the x is delta, 2 delta, 3 delta, and the 4 delta, we are in the same value as the exponential random variable. Geometric random variable's value is equal to the exponential random variable value. But we have something like this stepwise pattern for the geometric random variable, right? And that's what this equation means. Then what I'm going to do is that I'm going to look at a sequence of the systems such that the delta goes to 0. I'm going to choose a very sufficiently small delta. Then what happens is that this delta, this is delta, and this is 2 delta, and so on, right? This is 3 delta, right? The length of the slot becomes very small and very small and very small, so we can have a more stepwise function is something like this stepwise, and then this stepwise, and then finally as the delta goes to 0, in the limits the geometric random variables converges to the exponential random variable. Right? And that's what we mean by that thing. Let's summarize that. So what I did is that I'm going to consider the geometric random variable for this delta parameterized system, and then my construction of the p delta, which is a success probability for each slot, was the 1 minus e to the minus lambda delta. That was my construction about the success probability. So if I construct this geometric random variable like this, then as delta goes to 0, this delta parameterized version of the geometric random variable converges to the exponential random variable with the parameter lambda. Why are we talking about this thing? Because since one may make a connection between the geometric random variable and the continuous domain in the exponential random variable, somehow we need to have a mathematical way of describing what is the relation between this geometric and the exponential random variable. And this is one way of describing, in a mathematical language, describing the relation between those two random variables. So it's good to know. Good.